we're looking at polar conics. In other words, conic sections, that's ellipses, parabolas, and hyperbolas in polar coordinates. Circles are super easy and don't fit into this exact setting, what I'm talking about here, incredibly well, but they're so easy that we can kind of treat them as special. But so we're gonna start with a geometric definition of a conic that's not a circle that people don't tend to know aren't as familiar with, and we don't teach it as much um, as the two focus definition. So it's exactly the parabola definition, but it shows how you can actually make one definition with just one adjustable parameter that gets you parabolas and ellipses and hyperbolas. Okay, so just like in the parabola situation, we have a focus F and a directrix L. So let me go down to the picture here. Let me make that a little smaller. And so the directrix is this line. It's about at x equals 2 in this picture. And the focus is always going to be the origin. So the focus is going to be at the origin. And that's going to make it simpler and polar, not surprisingly. And then you choose an eccentricity number. And that's familiar usually with ellipses. And then what it's going to be, as I said, it's going to look a lot like the parabola definition. The parabola definition is the case where e equals 1, where a random point on the ellipse, a random point you choose in the plane, will be on the conic if its distance to the focus is this fixed multiple of its distance to the directrix. So here's an example, diagrammatic, with e equals 1/2. And so here's the focus, it's going to be at the origin. Here's that directrix. Vertical line, we're going to slant it eventually, but it's going to be vertical for a little while. And we're saying A gets to be counted on this curve if the distance from that point, I called it A here, I should have really called it P. This is P. If that distance to the focus is exactly 1/2 of its distance to that line. So this, of course, because this is a vertical, this is always going to be measured horizontally. It's a really sort of dropping in a horizontal altitude to the directrix. And this is just a straight line distance between 2 points. So let me show you a dynamic version of that. Okay, I think I changed it to P in the dynamic version. Okay. And so here I've got eccentricity locked in at 0.5. D is going to be our parameter that tells us how far the focus is from the directrix. So that's 2 here. And then what we see is that it makes sense that if I constrain the point in question has to be half as far from this fixed focus at the origin as it is from the line. That means in here, it's going to be generally about 1/3 of the way from the focus to the line. Okay, because I have a 2-to-1 ratio. As it goes around, it is getting further and further both from the focus and the line, but it can't do that. It has to do that in a particular way. Notice over here, I can't get very far. I can't get super far. If I go really far to the left, the distance from to the focus and the line will be very similar to each other. The ratio is no way can be 2-to-1. And so it says I can only go to here, which happens to be at -2. Oh, here's where I'm 2 units from the focus and 4 units from the directrix. How nice. And then symmetrically, I come around here. So it's not obvious at all. I think this is a perfect ellipse, but it makes sense that it's going to be bounded here. I can't get too close to the directrix, or the condition of being the 2-to-1 ratio is going to be violated. And also can't get too far either. Okay, so that's an example with e equals 0.5. Let's look at what happens. Of course, e equals 1. E equals 1 is a parabola. This is a definition that most people are familiar with. That's where the distance from the point on the parabola to the focus is exactly equal to its distance from the directrix, and that requires you to be on a parabola. The vertex then is exactly equidistant between the focus and the directrix. And then the really cool thing is that allows hyperbolas to come in as well. Now I've got something where I'm further from the focus than I am from the directrix. And notice I'm getting pretty close to the directrix and further from the focus here. And if that ratio is always here, it's about 2, then as I go up, 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 I've got to go out, 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 and pretty quickly. That as I go up and I'm increasing my distance from the from the focus, I've also got to increase how far left I'm going to be proportionally far away from the directrix. So again, not something that's obviously going to make a familiar shape if you're familiar with any other definition of a hyperbola, but it's pretty cool that it does actually make that shape. So let's go back. So what we get is that if E is between 0 and 1, it's an ellipse. And this is the usual, it turns out to coincide. It's not the usual definition you've seen maybe, but it coincides with the usual definition of the eccentricity in that case. That is a definition that talks about the two foci, the two focus definition. This is a different one where there's only one focus we're using, and we're using the directrix instead. But it turns out to be exactly the same eccentricity measurement. E equals 1 just gives you a parabola because it gets you back to the usual definition. And E greater than 1 is a hyperbola. And so there is a notion of the eccentricity of a hyperbola that fits very, very nicely in this family. Okay. In Stewart, for example, or in any other book, you'll see about a page of algebra to connect that with the like x squared over a squared plus or minus y squared over b squared. I'll let the book take care of that. But what I want to show is how if we believe this alternate definition, geometrically, it super easily gives you the polar equation for a conic. And then we can play with those, and it's a very useful thing, and turns out to be way more useful for like describing orbits of planets and things than the Cartesian equation. So we'll stay in this special case that I was just showing where the directrix is vertical. We'll say it happens to be on the right of the focus. So the D is always going to be positive for us. It's a distance from focus to directrix. And we're going to say x equals d, so not minus d. So this is the situation we got in here. So here was x equals 2. And the focus for us is always going to be the origin, or else it'll just be much messier. Okay, so we have a variable point P with coordinates x and y. And I just need to calculate both sides of this guy in terms of x, y, and or r, and then try to get everything in terms of r and theta to make it polar. Won't be hard at all. So the distance from the point to the focus, by definition, is r. The focus is the origin. Variable point is distance from the origin, is r. And then the distance from P to L, that's pretty darn easy, is just the difference of the x coordinates. If I've got a point A, like here at x coordinate about -1, how far is it from a vertical line? Well, Cartesian coordinates is the best way to do that. That's just about 3 because it's the difference of the x equals 2 and the x equals -1. So it's just d minus x. Really easy. Okay, so let's put that together and convert the 1x that'll appear in it excuse me, into polar. So here's the condition that distance from point to focus is eccentricity times distance of point to directrix. And now I'm just going to put that in. Ooh, now this is ever so slightly tricky because r is appearing on both sides. But there's this thing called algebra, which will let us regroup. So I'm going to distribute that, move the r's on to be on one side of the equation. There's a lot of letters here, but the algebra we're doing is really pretty easy. We're going to factor the r. And then we're done. This is a very common thing when you've got just like linear equation in variable r and just collect and rewrite. Okay. Yay. Okay, that's pretty cool. So if I input the d, again, which was the distance between focus and directrix, and the eccentricity e, then this is going to give me at least one version. I'll show you some other versions, but this is the simplest version of the polar equation for a conic. Pretty groovy. Notice that if e is less than 1, note if e is 0, I just get a dot because the top vanishes. That's why one reason why this can't describe a circle, this exact kind of formula. But if it's between 0 and 1, then we're nicely protected from r ever blowing up because e cosine theta will definitely be strictly less than 1, and the denominator will never vanish. Oh, that's good because in that case it's supposed to be an ellipse. I sweep the radar beam around in all directions around the focus, it should never go off to infinity. But if E is 1, excuse me, E is 1 or bigger than 1, heck yeah, this guy can blow up, and that's good because parabolas and hyperbolas do go off to infinity. The radar beam should say, hey, that spaceship or whatever is zooming away off to infinity in some direction. Okay, so no infinity, and if E is greater than or equal to 1, then R will go off to infinity for some theta values. Absolutely as it should, not a bad thing. Okay, real quick, if you still had a vertical directrix on the left and x was minus d, it's just really easy to redo. There's just like one sign that flips, and it turns out it flips this sign here. Okay. If it's a horizontal directrix, you often want to have these guys. And it happens to be, this is a plus, and it happens to be on the top, then it shouldn't be shocking that you take the original formula with a plus, but you change the cosine to a sine. And if the horizontal directrix is on the bottom, y is this negative value, then we get a minus. Okay, but there's a better way to combine all those formulas and more. So let me go back to the dynamic picture. One of the things I have here is I can move this guy and I can rotate this guy. Okay, so I can rotate. This is something that's hard to do. It's not impossible in Cartesian. Let me show you for an ellipse as well. It's not impossible to rotate conics in Cartesian, but we usually skip that section because we don't absolutely need it until around this point. But boy, it's really nice to be able to rotate these guys. And in polar coordinates, it's super easy to rotate shapes because rotation is all what polar is all about. If I want to rotate stuff, I just change the theta values. So all that I have to do to relate this standard ellipse to something that's like rotated 45 degrees, I want the exact same R values. I just want them to happen 45 degrees later in the cycle. So what that means is that in any, this is true for any polar equations, if you want to rotate by some angle, you just replace theta in your equation by theta minus theta naught. Okay, so it's the analog of a horizontal shift in Cartesian. That's really easy to do in Cartesian. You just shift the input values. Well, here, if you shift the input values in polar, those are angles, and you're going to be rotating. So this actually subsumes all of these versions. So I'll go back to the original version. You don't really need these 4 versions if you use this guy. I'm just going to put in a theta minus theta naught. Okay, so now there's 3 parameters. Eccentricity, which is the crucial one, it determines what kind of thing it is, how stretchy it is, the shape of the hyperbola, if it's hyperbola. There's the d, which is just a size factor that tells you how far your directrix is and just going to make it bigger or smaller. And then the theta naught gives you basically the direction of the axis. So back to the dynamic picture one more time. As I rotate this around, I'm just changing the theta naught. This would be theta naught is 0, 90, 180, 270, or pi over 4, pi over 2, or I should say radians probably. Okay. And then the d, I didn't really play the d much because it's kind of the least interesting guy. It's just going to make it bigger or smaller, but not change the shape, right? I could make it a hyperbola. I can make it hug really close to that focus or far. And any of these I can rotate by any amount. And again, here's our master formula. Works for all conics as long as, well, as it's not a circle, but circles are so easy. And of course, one focus must be at the origin. Cool.